So in this video, what I'm going to do is I'm going to show how you can estimate the parameters of retention models, where we start with the one-segment retention model, then we move to a two-segment geometric model, and then we then show how you can estimate the parameters for another two set of models that allow for richer unobserved heterogeneity across the customers and potentially across time. So the one segment model, again, this is assuming that every single customer shares the same propensity to remain with the firm. So if we were to assume that every customer had a 20% chance of churning in a given period, assuming they were alive in the period before, then the expected proportion of the cohort that's alive at any point in time would be 1 minus p raised to the power of t. And so we can see that's all that's happening over here. Now the sum of the squared errors are the differences between the actual retention curve and the expected retention curve. And so what we're going to do is we're going to get the sum of all of those squared errors across our training data, which we're assuming to be up to and including month number 7, and we're going to find the value of p that makes that as small as possible. So let's go to solver. I am trying to minimize the sum of the squared error over the training period data by changing p, where I know that p has to be between 0 and 1. So if I hit solve, again we can see we're doing the best job that we can under the constraints of a one-segment model. Now the two-segment model is allowing for there to be 2 coins, and then there's some probability that someone gets the good coin versus the bad coin. And so pi represents the probability of getting P1, and then if I don't get P1, I get P2. And so I've got these segment-specific survival curves, which is just 1 minus P1 raised to the power of t, 1 minus P2 raised to the power of t. And if I knew those, and I knew the mix of customers that would get P1 versus P2, then the expected cohort level survival curve would be just a weighted average of these two segment-specific survival curves. So this is my new expected percent alive that I then compare to the actual retention data, and I'm just going to do the same thing as before. So I'm going to find the values for these 3 parameters that make the sum of the squared error as small as possible. It's the same general constraints as before. Here I'm just going to be a little bit more exacting, just to have these boundaries be just a smidge greater than 0 and a smidge less than 1, just to avoid any numerical issues. So we can see we've done a lot better here. Now, the third model I'm going to introduce is called the shifted beta geometric, and this is where we assume that the coin that someone gets is basically a random draw from the beta distribution. Once they have their coin, then we have exactly the same coin flipping story that we told before. So there's a more complicated formula for the survival curve, but ultimately that's what's going on under the hood. And just like with these other 2 models, we're going to estimate the parameters that give us the retention curve that's as close as possible in the training data to what we actually observe. And so the only other thing that I would note is that the only constraint that we put on alpha and beta is that they must be strictly greater than 0. So they can't be 0, they can't be less than 0, but they could be 5. That's what we see over here. So I'm going to set my objective to be the SSE over the training period data. I'm going to change alpha and beta, and I'm going to impose this constraint that these 2 parameters need to be strictly greater than 0. Now the cool thing is, this model is actually simpler from a parametric perspective than the 2-segment model. It has 2 parameters, whereas the 2-segment model has 3 parameters. And what's really cool is we can see that we're doing a really good job here of capturing that calibration period data, and our forecast is really quite good. We can see that the 2-segment model is slightly over forecasting by the end of the data set. The SBG model is slightly under forecasting. How about the Weibull-Gamma? So what is the Weibull-Gamma? It basically makes a very similar assumption to the shifted beta geometric, that the coin that everyone is born with is coming from a continuous distribution. But once they have that coin, it can get a little headsier or a little tailsier over time. And the way that we capture time dynamics is through this parameter c. So maybe a good way that I can show this is I'm going to first, and then I'm going to show what happens if we change c to be bigger than 1 or smaller than 1. So I'm just going to go here, go to solver. I'm again minimizing the sum of the squared error, changing these parameters. The only constraint I need to impose is that they're all strictly greater than 0. It's already been done. When we do that, we are almost rock solid, right on the money. So again, still not quite perfect, but that's still pretty darn good. Now what we can see is the C parameter is 1.89, and what that means is that the coins that everyone was born with, they kind of get worse and worse over time. We can see that if we made C equal to 0.9, that would lead to a much more optimistic projection for the future. So let's make it 0.8. You can see now we're way over. And so again, that's just kind of an indication that what C does is it says with the passage of time, everyone's coins are going to vary. And they're going to get either a little better or a little worse. If C is equal to 1, then everyone's coin stays the same as it originally was. And this collapses to then a model that's very similar to the SBG. Now, the question is, how good of a job did these models do? And one way that we can measure that is through what's called the holdout mean squared error. And what this is going to do is it's going to basically get the average error over the holdout period. So again, in the calibration period, in the training data, more parametrically complex models are naturally going to perform better, but they could overfit. And so a big question is, well, how do these models do on data that we have held out in time? And so it's a very helpful thing to focus on to evaluate how good a job a particular model is doing. So we can see here the holdout error, the holdout MSE for the one segment model is 1.52%. The holdout MSE for the two segment model is equal to 0.0. Well, we're not perfect. Technically 0.38%. How about for the SBG model? .47, so slightly worse than the two-segment model. And now how about for the Weibull-Gamma model, which again has 3 parameters. This one has the same number of parameters as the two-segment model. The SBG had 1 fewer. So here we can see the MSE is 0.0076%. So if we just wanted to get all of these errors in a little table, we can put that SBG 2-segment. So the 1 segment is 1.519, 2-segment is 0.038, SBG is 0.047. So I'm just going to make the formatting the same. So what we can see is the 2-segment model brings about like a 10x or much larger than that actually reduction in error. But we can see that the SBG model is kind of comparable to the 2-segment model despite having 1 fewer parameters. And the Weibull-Gamma model has even a much lower error than either of these 2 models. So again, hopefully this makes sense. You can see the estimation procedure is virtually the same for all 3 of these models. So hopefully once you have this spreadsheet, you should be in pretty good shape to run this model. Now the nice thing about the Weibull-Gamma is it also allows for covariates. So that's not something we're going to cover in this video. Unique to this model relative to the other 3, and gives us a lot more flexibility to accommodate things like different customers coming through different acquisition channels having different propensities to remain, or that there's things that happen over time that we would be able to control for. So thanks for watching, and if you have any questions, give me a holler.